Here is a second example of statistics, and in this particular example we're going to do something called goodness of fit. You start out with the rivers data set. Here it is. If you want to find out a little bit about rivers, you just type question mark rivers or help rivers, either way. And these are the lengths of 141 major rivers in North America compiled by the U.S. Geological Survey. So you can see there are 141 elements in this vector, and what we'd like to do is see how well the exponential distribution fits the lengths of these rivers. So let's start out with a graphic here, and the graphic I'm going to do is the empirical cumulative distribution function. Plot.ecdf will display that. We want to do that with rivers. And when we do, we get all of these dots here at the 141 points. Not so good. So I'm going to show you one way of getting rid of those dots. I'm going to do an up arrow, and I'm going to add two extra parameters. Verticals equals true, and another parameter, PCH, which we've seen before is the plotting character, and I'm going to have a plotting character of nothing. So when you do that, you now get this function over here in the lower right. Basically what you have there is for each of the data values, and there are 141 of them, each time it encounters a data value along the horizontal axis, it will jump up by 1 over n, and in our case n is equal to 141. So this takes a tiny little step upwards of 1 over 141 each time it encounters a data value. And that's called the empirical cumulative distribution function. Well, we're interested in seeing how well this fits the exponential distribution. So let me set a parameter called MLE to the reciprocal of the mean of the rivers data set. So if you take a look at MLE, it's going to be 1 over whatever the mean is of those 141 values up there, and that reciprocal is 0.00169. Now, next thing we want to do is we want to set an x vector and a y vector, because we're going to plot the fitted exponential, and then we're going to run a formal goodness of fit test. So the x vector will be a sequence which starts at 0 and goes up to the max of the data set, the largest value in rivers, and I'm just looking here. I don't think there's one that's bigger than 2348, but there's got to be, because it takes a jump out here that's over 3,000. There it is, 3710. That seems to be the maximum. So we're going to set up a vector that goes from 0 to 3710, and that particular vector will have a length, and you can choose any number in here. I'm going to choose a larger rather than a smaller number, maybe of 300. So it'll have 300 elements to it, and x has been set. Then what we want to do is have y be the cumulative distribution function, that's p, for the exponential distribution, and put in the values x that we created just above, and use the MLE value as we create y. Finally, if you want to see what x versus y looks like, this is the fitted exponential distribution. It looks like that. Now, if you've done a lot of data fitting, you recognize right away that there are some problems there. That's not a great fit. But the next person might look at it and say, yeah, that's a pretty good fit. So what you've got to do is you want to run a statistical goodness of fit test that will allow you to say whether this is a good or a bad fit. And that, or I shouldn't say that, one of the good fits is KS.test. KS stands for Kolmogorov-Smirnov, and this is going to tell us if we have a good fit. This is the one sample Kolmogorov-Smirnov test. So we're going to take rivers, and it's looking for the distribution here. We're going to say use the CDF of an exponential as the comparison, and then finally put in the MLE. So once you do that, it will come back, and you can see down in red it's going to complain a little bit. And what it doesn't like is it doesn't like tide values. So it's going to do its best no matter what, but somewhere in here there are a bunch of tide values. And I don't see any right off the top, but I'm sure they're in there because it's complaining about them. And so what we get in this case is we get a maximum difference of 0.28. Now this 0.28 is occurring probably right about where the cursor is, right about here. That's the largest vertical distance between the empirical cumulative distribution function and the fitted distribution. Somewhere in this area right here, there's a maximum vertical distance of 0.28. This gives us a p-value that is very, very small, 2.3 times 10 to the minus 10th. So there is overwhelming evidence here that the length of rivers that is in the built-in data set rivers is not well modeled by an exponential distribution. So we should try a different distribution if we want to fit a distribution to this, maybe the Weibull or some other. The Kolmogorov-Smirnov test is one of the more basic goodness of fit tests. There are others that could have been used here. We could have binned the observation and tried a chi-squared goodness of fit test. We could have used the Anderson-Darling test or used the Kramer-von Mises test. Any of those are good alternatives to the Kolmogorov-Smirnov test. So this ends a second example of using statistics in R. The first example dealt with confidence intervals, and this one dealt with goodness of fit tests. The next and last section we're going to do will do regression.